Okay, cool. So before anything, let me tell you a story from ancient Greek mythology. This is the fight between Hercules and the Hydra of Lerna. Hercules commits a very serious sin. He was remorseful. He felt a deep pain in his heart. So to be forgiven and live in peace, he was ordered to complete 12 hard labors, of which killing the Hydra was only the second one. The Hydra had several heads and very strong regenerative power, so that every time Hercules chopped off one of the Hydra's heads, out of the wound, almost immediately one or even more heads would appear. So it was really hard to kill the Hydra. But Iolaus, also in the picture, found a workaround. Whenever a head was cut, using his torch, he would cauterize the wound, and that would prevent new heads from forming. So eventually, Hercules managed to slay the Hydra. So I'm telling that story because that's the origin of the expression in Portuguese, bicho de sete cabeças, or seven-headed beast. But not to be confused with the story of seven-headed beast that appears in the last book of the Bible, the book of Revelations. Sorry, Bruce, this is another beast. Okay? The expression figuratively refers to hard problems with complex solutions like killing the Hydra, but is mostly used in negative form. Não é bicho de sete cabeças. It's not a seven-headed beast. And we use the expression to explain that certain things are not as complicated as they might seem. So in this presentation, I'm going to show you a problem and the solution I came up with. And I hope to convince you that at least the problem não é bicho de sete cabeças, it's not a seven-headed beast. But I guess the most used English expression that conveys the exact message is it's not rocket science. So I hope to convince you that this problem is not a rocket science. So, thanks for attending my talk or for watching the video recording. My name is Cassio Neri. I'm PhD in mathematics, but currently I work in finance in London. But this work here was carried out in my spare time, has nothing to do with my current or previous employer. I'm here in a personal capacity, and all the opinions I'm going to express are mine and do not necessarily reflect that of my employer. So, the problem we are interested in is the conversion between float point numbers and a string. And standard C++ offers at least 6 ways of doing that. But avoid the first 2, they are not safe. But my point here is not to show them all, it's just to point out there are more than one way, and the output is different depending on which functionality you use. And the reason for that is there is no one-size-fits-all solution for this problem. We have different trade-offs between customization and performance. This talk is more about performance, so I'll be talking more about what goes behind the scenes of two chars, and especially the output of two chars. Yes?
What's unsafe about the second one?
It's type unsafe. I put %G for double, but maybe I mess up the type and I put an int there, and so the compiler might go and parse the string and give you a very good warning about that, but not all compilers do. Okay, but it's type unsafe. The buffer overrun, etc., is still there if the type doesn't have the same size as the one that is described in the format string. Okay, so but this thing, there are more than one way and the output is different, is not particular to C++. Here are examples in Python, JavaScript, Java, Rust, and C#. And particularly interesting is the case of JavaScript, because JavaScript make almost no distinction between integers and float point numbers. Basically, all numbers are float point numbers. So an awful lot of numbers that you see on a web page might come through this algorithm, might go through this conversion. And also a spreadsheet application, virtually all numbers that you see on a spreadsheet goes through this one of these algorithms. So it's very important to be efficient. So what's the deal? Okay, we know the computers, they store numbers in binary and we want to see them in decimal. But we all know how to convert binary to decimal, right? It's just a bunch of divisions and modulus operations by 10. We extract each digit, and from each digit, we get the char, and that's it. Easy peasy, right? And here is the code. Some code that does that. So yes, this problem on its own is a very important problem. There are some clever people that come up with very good optimizations or new algorithms to perform that, notably Andrei Alexander's school, but that's not the problem we are talking about. We are talking about float point numbers, and this here is from integers to a string. It's a different problem. Is it? Okay. Take a look at that. This is the minimum strictly positive float, 2 to negative 149. It has awful number. It has 149 digits after the dot. So how do we calculate this number? Do we run the loop that I showed you? By the way, the loop, the code I show is just a textbook just to show you how to do, but it's not what is done in practice, right? But should I run this loop 149 to calculate each of these digits? That sounds quite expensive, right? And on top of that, we don't want to see that number. It's an awful number. Imagine a spreadsheet full of those numbers. What we want to do is to see something like that. Okay? But how do we get this? Maybe we have to calculate this whole number, and maybe to calculate this whole number, we need some kind of multi-precision library or big num type just to calculate this number, and then realize, okay, there is one position 45 after the dot. We can just print 10 to negative 45, and the user will be happy. Let's throw away all these digits that we calculated. It sounds wasteful. So there are other ways of doing that. Okay, the point I want to make here is this. I want to give you the feel that most people, at least happen to me, that consider that problem go through. So first we think, it's trivial. Just division by 10, modulus by 10, done. Oh no, it's not that trivial. I have no idea how to do that. That's very difficult. That's very impossible. That sounds impossible. How do the guys did that before? And then one day, something click, you see the light at the end of the tunnel. Or should I say, the light at the entrance of the cavern, the cave. Let's talk about that later. So I'll show you how to do that in a better way. But for that, I need to explain how float point numbers are stored in a computer. So I start with a very simple computer, not our Intel AMD x86 computers, a mechanical counter like that. You might have something like that. At least in Britain, we have a lot of people have at home electricity meters or gas meters that have a dial like that. So it's a mechanical counter that this one here is store 4 digits from 0 to 9, so it can store any integer between 0 and 9999, right? But my counter, my electricity counter, needs also to show fractional parts, not only integers. So how do we solve this problem? How we can turn this thing that is capable of storing integer in something that is able to display fractional numbers? So the mechanical engineers, they come up with a brilliant idea. It's a very interesting piece of technology. Look at that. Do you see that? If you didn't, it's there. They stick a dot in between digits, okay? There is no mechanics behind the thing. Is still the same mechanics. It's just one conceptual dot that is there just for us, okay? So we'll come back at these conceptual things many times. So there we are, we have an integer representation, and we stick a dot in between digits. And again, the dot I'm graying out because it's just conceptual. It has no meaning in the mechanics or in the semantics behind the scenes, at least as far as counting up and down is concerned. If I do multiplication, division, that's another story. But let's concentrate just in going up and down, or just going up to make me think simpler. So we can start increasing in steps of 0.01, and let me speed up, and then we can go up to 99.99. Okay, yeah, nice, but what if I want a larger range? 99.99 is not enough. I want to go to a larger range. Of course, I can add an extra digit, but that has an extra cost. So with the resource that we have, how can I make the range larger? So what I suggest, we repurpose the first digit. We look the first digit as the exponent in that expression, okay? And the remaining digits is what we call the mantissa. So let's see how it goes. And on the bottom, I'll put the number in fixed notation just for us to understand what number we are representing. So again, we can start counting in steps of 0.01. Let me speed up and let me make a pause here. If I keep going exactly as we were doing with when we have the integer, the next step would reset the mantissa and increase the exponent, right? We would go to this number, but this number is 0. We don't want to go back to 0. We don't want to have several representations for 0, okay? Because if I do that, for every exponent, we'll have one representation for 0, which is when the mantissa is 0. We don't want to do that. So here we have, okay, the parts grayed out are conceptual, but here we have to make something different in our logic. Here we have to introduce this rule. When the exponent is non-zero, the mantissa first digit must be non-zero as well. So if a number of that format is what we call scientific notation, right? So let's keep going so we can increase. Let's speed up and see. Now we can see that the steps, the speed of increasing is increasing. So and it grows, the step between two numbers grows when the exponent grows. It speeds up, it accelerates when the exponent goes. And then we reach the maximum, which is almost 9 billion, or 10 billion, almost 10 billion. That's good. So from 100, we went to almost 10 billion without extra cost. Just a little bit difference in the logic, but no extra cost. It's still the cost is storing four-digit numbers. But I'm still not happy on the small scale. We start in steps of 0.01. Maybe it's too much. Maybe I want to go in steps, even smaller steps. And I'm happy to trade the big range, so not go as large as 10 billion, decrease the range, but increase the resolution. So I can rescale everything by, say, 10 to the negative third. I don't know, pay attention, this is just equivalent of moving the dot 3 positions to the left. And again, everything that is gray out is just conceptual. It's not stored in any shape or form. It's just conceptual. But rescaling like that is the same as biasing the exponent, right? So I'm just biasing the exponent, it's the same thing. So let's see how it goes now. So now we start in steps of 10 to the minus 5. Before it was 10 to the minus 2, now it's 10 to negative 5. So it's much more granular, the steps. Going up, let's go faster, and then we reach almost 10 million with a very small granularity when we are dealing with small numbers. So that's basically how decimal float point representation works. But the computers are binary. Our digital computers are digital, they are binary. So it's essentially the same thing. We have the exponent, the bias exponent, we have the bias, we have the mantissa. The base now is 2, is not 10. I'm not showing you the... So to be perfect correct, I should put the mantissa in binary. I should use subindex 2 here. That's the notation for binary. But I'm using notation here just to make the slide simpler. But they are in fixed font format to denote they are binary numbers. So the 2 is not a binary number, but the exponent and the mantissa are in binary. And I'm not putting here the number, the corresponding number in fixed notation, but instead I'm putting the real line and the place of the number on the real line. So there we have 0. And let's do our counting. So we start counting binary, increasing. Let's stop here. Remember that we cannot reset the mantissa because otherwise we go back to 0. So we have the same rule that we had before with a twist. Now, the rule is if the bias exponent is non-zero, then the mantissa first bit, not digit, first bit is also non-zero. But if a bit is not 0, it must be 1. And a number in that form, we say that is a normal number. And those that we saw before when we had the 0 here, they were not normal. They were some called subnormal or denormalized number. Okay, so normals are for binary what scientific notation is for decimals, just that. And we can increase. And now, pay attention to the gaps between two consecutive float point numbers. It starts increasing as they step when we saw the decimals. It's increasing, and every time the exponent gets increased, they step between two consecutive float point numbers increase. So that makes a distinction between what I call centered values and uncentered values. Centered values are like this one. It's halfway between its two neighbors. But for each exponent, the first float point corresponds to exponent. The distance between the next one is double the distance from the previous one. So those are uncentered values. And this is particularly important for our algorithms because most of them, if not all, they have a branch. So if it's a centered value, go this path, otherwise go to the other path. So it's important to understand the difference between these two types of values. But in this presentation, I'm going to focus on the centered values, just to make things simpler. Okay? So, yeah, finally, you might not have seen, but most of the time, so just when the bias exponent 0, this guy can be 0. Otherwise, it's always 1. Most of the time is 1. We can figure out that is 1 or 0 from the exponent. So it's really wasteful if you just store this thing that is almost always 1. So some representations do store the 1, like the Intel extended representation. It does store this 1 because that might make the circuitry simpler, but from the point of view of memory, we really don't want to waste this bit. So for instance, the IEEE representation doesn't store this bit, is implied. So again, it's something else that is conceptual. It's implied from the bias exponent. Okay, so this is basically the theory behind the float point numbers representation. I'm just sparing some details about nums and infinities and etc. But what is missing is just details. How many bits we use for the mantissa, how many bits we use for the exponent. So, and that's where the IEEE 754 standard comes in. It sets this number of bits in each possible representation. So, and it describes 3 binary representations: binary 32, aka floats; binary 64, aka doubles; binary 128, __ float 128, support by Clang and GCC, but not Visual Studio. And we have also the new types. They are not type defs for the others. They have to be different types, but they, behind the scenes, conceptually, they are exactly the same. So let me just show you one of these representations, the binary 32. It would be more useful maybe to present binary 64, but there are too many bits, they don't fit on my slide. So I'm using binary 32 just because it's shorter, the bits fit on my slide. And so let's see how we can decode this number in binary and see what is the real value of this number. So first, the standard says that the 23 rightmost bits should store the mantissa. 8 bits for the bias exponent And something that I didn't mention before is the 1 bit for the sign, because of course we want to represent positive and negative numbers. So let's decode this one. It's starting with the sign. The rule is very simple. If the bit is 0, then it's plus. If the bit is 1, then it's minus. Here we have 0, so it is a plus. Now let's look at the bias exponent. So it's a bias exponent. To get the exponent, we have to remove the bias. And so pay attention again, the bias exponent here is non-zero, so it's a normal number. And if it's a normal number, then the bias has this pattern here, 0 and then 1, 1, 1, 1, or in that case, 127 for normals and 126 for subnormals, but not forget about the subnormals. We're not going to talk much about that. So the bias is 127, and I did the subtraction there. I subtract the bias from the bias exponent. I got the exponent in binary. So our number is start take shape. I put here the 1 because the bias exponent is non-zero, so it's a normal number. So if it's a normal number, the mantissa first bit is 1. So it's implicit 1. And what about the remaining digits of the mantissa? They are stored in memory or in a register. So that's the number that we have. You can do this calculation, but let's decimalize a little bit to make it easier for us. So that's the number. It's 2 to the third times 1.34375. You might do this calculation and see what the number is. But there is one thing here that I don't like, and because I don't like for the point of view of the algorithms that I'm going to explain to you, not only mine, but the others, especially the most modern ones, they don't want to work on fractional numbers. And our mantissa here is fractional. So how can we turn the mantissa into an integer number? Easy. If I double the mantissa, to keep the same number, I have to decrease the exponent. I just decrease the exponent. So let's see again. Double mantissa, decrease the exponent. Is still the same number. And still the same number. Let's make a stop here, because then now we have 10 to the 0, which is 1, times this number. So that's the number we're representing here. It's 10.75. Okay, but it's still not an integer number, the mantissa. So let's keep going. Now we have an integer mantissa, but we have an integer mantissa for this example. If I had a 1 here, it will still be a fractional number. So we have to move the dot until we are sure that there will be no 0 on its right. And the only way to be sure there will be no 0 on its right for any possible input is to move the dot all the way to the right. So that's the number that we have. We are going to work with this number. So the takeaway from this slide is, from the binary pattern, we extract 3 pieces of information. The sign, the exponent of the base 2, and then the integer mantissa. The sign, when I'm going to create the string, I can just see if it's a minus, I put the minus char before. If not, I just don't put anything. So it's not really a concern. But it's there, we have to extract this information, okay? So that's the takeaway from this slide. Now let's take a quiz. But it's not a trick C++ question, I promise you. So what I'm doing is, I'm initialize a double with 1 divided by 3, 1/3. Just initialize that, and then I print on the screen, okay? Again, it's not a C++ trick question. It's not about what format does. Just think, if you don't know format, just think, I initialize a double with 1/3 and I print on the screen. What do you expect to see? So here I have 5 options. Option B and C are very similar, so I'm highlighting the difference. Is the last digit. B is, the last digit is 3, for C is 4. So show of hands, who thinks that is going to display 0.3? Nobody. Who thinks is going to present B, like 0.333? A few people, maybe the majority. Who thinks is C? 2, 3, 4. Fewer than B. who thinks is going to print the two words 1/3? Nobody. Or something else. What do you think?
I didn't count the digits, but it seems an arbitrary number of digits in B and C, and it seems unlikely that it will be one of B or C.
Okay, let's see. It is going to be B. So most of people got it right. It will print at some point and it stopped at some point. It turns out it's exactly the same number of digits it prints because of some rules that go behind the scenes. Okay, say almost same thing now, but instead of a double, I have a float. I initialize the float to 1/3 and then I print the output. And the options are basically the same. The difference is because float has less precision, so it might print fewer digits, okay? So that's the only difference between the first case. So who thinks is A? None. B? C? 2 people, so majority for B. D? Nobody. Something else? Nobody. Huh? That's it. That's it. That's right. That's what gets printed. I don't know, probably those who vote for B first and B second will be very surprised, as I was when I saw that, but then later realize, looking deep into details, why it was C. It makes sense. The problem, we are thinking in decimal. We are thinking like humans. We are saying, okay, the next digit will be 3. It's closer to that one than that one. We should round down, we should get B, but that's not how it works.
This is because this format function computes the number of digits that it needs, so that when it reads it back in, it'll get the same representation it started with?
No, it's not because of it doesn't decide per se the number of digits, let's say in advance. It will decide somehow the number of bits, but it will make other decisions and we'll end up like that. Let's dig deeper. Okay, so let's see what happens. And by the way, same thing in other language. It's not same thing particular to C++. So it's not format. It's just how float point numbers work. So here is our number, 1/3 on the real line. I put a lot of digits there, and I put the bar to say it's repeating trees. Okay, so that's the number 1/3 that we have in mind. That's the number that I type in the source code, 1 divided by 3. Or I could have typed 0.33333, will be exactly the same. That's the number that we had in our heads, and it can be conveniently written in this format here. I leave you to prove that this equality holds. And you might find, why are you writing in this format? Remember from when we decode the binaries, the bits into the value, we realize we have always something like power of 2 times an integer mantissa. And here are 2 consecutive numbers in that form, and actually are the 2 neighboring representable float point numbers on the neighbor of 1/3. So nothing in between these 2 on the top and on the bottom is representable by a float point number. And the number that we ask the compiler to store is not representable. 1/3 is not representable, but I wrote in that format here, then we can easily see that it's closer to the one on the top than to the one on the bottom. That's why the compiler tells the CPU actually store the number on the top. That's the number that CPU ends up storing, although I typed 1 divided by 3, but that's not impossible for the CPU to store that number. And then the code asks, now print that number. So and how the algorithm decides what to print? First of all, forget the 1/3. 1/3 is not representable. The CPU never heard about 1/3. It doesn't know it exists. It exists this one, and exists that one. Okay, maybe when it's going to print the string, it might do some in-string manipulation. But that's it. It only cares about the numbers it stores and it can also look at the neighboring numbers. So this one, and there is also the next one, but I didn't put on this slide just to make it shorter. And when the algorithm is going to print something that at least disambiguates between the one that is really storing and the neighboring ones. So how can it do that? It can go digit by digit until it finds something that can disambiguate between the two. And then found the 4 there and the 3 here. Sorry, and the 1 here. And that's the side, okay, I will truncate here and print 0.3333 to 4, which is yet another number. Okay, it's yet another number. It's not the number that it stores. It's not the number that I typed. But it's something close. So that's how we get the 4. If you do the same exercise with doubles, it ends up being a 3. You can do that and you'll see. So there's no magic here, and there is no rule like the rule that we humans use. Oh, if the next digit is 5 or more, we round up or round down. It's not that how it works. That's how it works. But this is just conceptually, okay? If I do that, and actually, at the very beginning, the algorithms were doing something like that, calculating the number and also the 2 neighboring and scanning the digits and then throwing away when they could see some disambiguator. Okay? Very wasteful. This is just conceptual for us. We can do better than that. So the title of the talk is A New Dragon in the Den. So here be dragons. I need to talk about the dragon's den. Is anyone from Britain here? No? So if I tell a British people the dragon's den, they'll think about this BBC program. It's a program where entrepreneurs, they pitch their ideas to wealth investors, the so-called dragons, to get an investment. It's actually a Japanese franchise. It runs in many countries. In Britain, it's called the Dragon's Den. I think in Canada is also Dragon's Den, but here in the US is the Shark Tank. So, but obviously that's not the Dragon's Den that I want to talk about. Okay, it's not the Dragon's Den. The one that is starting in 1999 when Steele and White published their paper. For me, the most important contribution was to give a precise statement of the problem, what the conversion should do, and they also published the first algorithm called the Dragon, and it's named after this fractal curve here, the Heway Dragon curve. And mathematically, there is no connection whatsoever between the algorithm and the curve. I will explain what the connection is. So the Dragon curve is built in a recursion in steps like that. So as you can see, in each step, there is always just a single path. You step 1 unit and then you turn either left or right 90 degrees. And then you step again and turn either left or right. So this path in each step can be described by just a sequence of letters, L for left or R for right, okay? But that's not how the description they saw the first time was in a American Science column by Martin Gardner, and he was using other letters. He was using F for fold and P for peak, never mind why that, but F and P, they thought, oh, F and P, float point, yes, let's call our algorithm the Dragon. It's not fun. It's not my fault. It's not even White. He distanced himself from this joke. He said, it's completely Steele's fault. I have nothing to do with that. But it is what it is. Let me move on because this curve is quite hypnotic. I see some people sleeping here. So in 96, Bergen and Dybvig, they improved a little bit the Dragon, but they didn't give a new name for the algorithm. Then 2010, Lloyd published Grisu. Grisu and Dragonbox is this little fella here. Is a Italian TV program for kids, and Grisu is from a traditional family of dragons, but despite that, he dreams to become a firefighter. Anyway, so Grisu, not the Dragonbox, but the algorithm, became very, very popular. It was 12 times faster than the Dragon. And is still used in V8 and SpiderMonkey, the most important JavaScript engine, so it means it is using the major browsers out there. And as I told you, doing that efficiently for the browsers is very, very important. But Grisu had one flaw. It could not produce the right result 100% of the time. There was 0.5% of the float point numbers that would produce the wrong result according to the rules set up by Steele and White. But it was clever enough to detect this corner case, and instead of producing the wrong result, it could just defer to the Dragon, to a slower algorithm. So that's basically what is done. Improve the situation, but is this 0.5% yet bugging many people? So Jaffa in 2013, he published his algorithm. I don't know much what he does. I don't know much about Jaffa. But then in 2016, Andres School and his PhD advisors from University of California, San Diego, they came up with Errol. Errol is this little dragon here from the fantasy book Guards by the British writer Terry Pratchett. Okay, so they named their dragon after this one here. And they fix Grisu flaw that could not produce the right result is this 0.5% of the time. So their Errol can produce the right output 100% of the time. Unfortunately, it's not faster than Grisu. As you can see, he crossed the faster in his title when he presented that in an ACM conference. So it was not faster. It didn't pick up. It didn't took the crowd from Grisu as the most popular one. Then in 2003, something very important happened. So Adams presents in another ACM conference his Ryu. Ryu is the Japanese word for dragon. And his main motivation, he said, okay, at some point, he went through the same kind of journey that I went through. So he thought, should be easy. Oh, I have no idea how to do that. Let me see what is there. Oh my God, it's so complicated. 10,000 lines of code for doing that. It must be a simpler way. So he tried to simplify. He came up with Ryu. And it's a very important algorithm. It was also mentioned in CppCon 2019 by Stefan T. Lawade, and I want you to, sorry, no, I don't want to go there. Oh my God. Sorry about that. Not yet. Not yet. Is this one? I have to press. Yes, now it is. So here what he said, and I quote, "Ulf Adams' magic is still beyond my understanding." Close quote. So we can all agree that Stefan is a very clever guy. If Stefan cannot understand everything about the algorithm, it's to tell something about the algorithm. And my humble opinion, I agree with him, is still very complicated for my opinion. But anyway, it became quite popular, it's picking up. There is more and more pieces of software using Ryu, including close, of course, Stefan implemented that in Microsoft standard template library, C++ standard library, but is also using GCC. And there's another dragon here, but this dragon is not on the scope of this talk. Okay, and then that's not the end of the story. In 2020, Juliet published Schubfa. He broke the tradition because Schubfa is not a name of a dragon. It's the German word for drawer. Am I right? Okay, so, and the point is he wants to refer to Dirichlet box principle. So the drawer and box and etc. And he called that Schubfa. It's still very complicated for me. But then, same year, Dion, he didn't know about Shubfa, so he came up with Grisu exact. So he picked up ideas from Grisu and ideas from Ryu, and he fixed the problem that Grisu had, and he came up with Grisu exact. But soon after he did that, realized, oh, there is this Shubfa thing, and then it was better, and then he came up with another one he called Dragonbox. So back to the tradition to give dragon-related names to the algorithm, and he put the box to refer to Shubfa, because he also picked up ideas from Shubfa to create Dragonbox. And Dragonbox he implemented himself in the FMT library. But there is a new dragon in this thing. So that's my dragon. I will tell you, but before I tell you, I have to explain exactly what is the dragon's problem. So there are 3 steps in this whole conversion from float point numbers to a string. The first step is the one that we saw in the binary 32 slide. So it's decoding. Just take the bits and extract the 3 pieces of information, the sign, the exponent, and the mantissa. And there is not much room for creativity here. It's just a bit twiddling. You might use AND instead of shifts and etc. So maybe you get one cycle better here, one cycle better there, but that's not much, say, mathematical room for mathematical creativity here. Then there is the second step. That's the dragon, okay? And the second step is basically what we did with 1/3 when I showed you what we would print. So going through this dish, then etc. If you think about that, what we did was from the input to -25 times this integer mantissa, we extract something where that was a power of 10 and the mantissa was 333333334. So that's what the dragon does. It converts from binary to decimal. And then there is another step. Once we have the integer exponent and the integer mantissa, then we run through one of these integer to string conversion, and then we print the number. So, but the dragon's problem is just the middle step of the thing. All the papers that those academics and practitioners, they publish, they explain their dragon, and it's always about this step here. So that's the dragon's problem. So let's take a step back and state that more precisely. And here I will give each step, I will be more precise. I state from a very high level overview, and then I will go deeper and deeper, but not all deep down to the very bottom of the algorithm. That will be a subject of academic paper that I hope to publish, soon, rather sooner than later. So, but the problem of the dragon is, so this is our number, is in that form, a mantissa times a power of 2, but then we have to convert that to a mantissa times a power of 10, right? But we have to pay attention to 4 bullet points. In decreasing order of importance, there has to be no information loss. It has to be as short as possible. It has to be as close as possible to the inputs, and some tie-break rules need to be applied. So let me go through some of these bullet points in more detail, so giving more precision. Remember when we print 1/3 also? We type 1/3, the computer changed the number and said something else for the computer, and the computer end up storing that number. That's in the memory of the computer. And then we said, please print that number. And then it printed a string similar to that. Okay, actually, there was the 0 point, blah, 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 but it was basically that string here. And that was a string. And then if we go and we type that string, or that 0.333334 in our source code. So we type the string, and then some parser, in that case our compiler, but could be a generic parser, it will read that string, calculate this number, parse this string, calculate the number, and then tell the computer to store some number, not necessarily the one that it just read, because that's what it did with my 1/3. It didn't tell the computer, please store 1/3, because it knows the computer cannot store 1/3. So the parser will do something, and then we'll come up with another number and we'll tell the CPU, store this number. And it turns out that is exactly the same number that we had at the first place. So that's the no-loss information. We want to have the round trip to succeed, but when the round trip starts from the computer, from one possible float point numbers. It doesn't work when I type 1/3 and I expect 1/3 back. It's not going to happen. But if the computer stores a number and go through this exercise here, it should get back the same number it had at first place. So to understand what the parser does, let me explain you, it's very simple. Here, this is the number that was stored and the number that the parser will tell the computer to store again. And here are the neighboring float point numbers. So the number that the string represents, if you remember from the previous slide, it was more or less here, 2/3 on the way between these two here. So it was here. So it's closer to this one than to any of the other two. And that will happen if the string that reads represent any number in this interval here that starts halfway between these two and ends halfway between these two here. So this is what I call the permissible interval. So actually our algorithm has to produce a string that represents a number in that interval, because then the parser, when parse and calculate this number, will tell the computer to store this one because it's the closest one.
So are you saying that the standard library's format function has the no information loss property by default?
Yes, by default, because you can,
Whereas the others on your list do not.
Yes, exactly. So two chars, I think two chars also you can choose the format between scientific notation and fixed notation. But when you decide for scientific notation, it will do exactly that. And as to the format, you have the brackets, and then you can put some format there, say I want 6 digits, blah, blah, so you can, but if you give the default, it falls back to call two chars, and then it does exactly that. So it has to produce something inside this interval. So I didn't say yet exactly this number. Okay, in that case, yes, but I will explain later on better how to get the real number in every case. Okay, but that's exactly what it does. So, but what happens if the string happens to be exactly the midpoint halfway between two? My last bullet point was tie-break rules. There will be a tie-break rule that says, so in that case, prefer either this or that. It can be round up, round down, round towards infinity, towards zero, and etc. The most popular one is round to even. And I think the standard says that two chars should use round to even, which favors even mantissas. So another reason we have to work with integer mantissas, right? Because if I have a fractional mantissa, it makes no sense of talking about an even number, right? So that's another reason why we have to work with with integer mantissas. So in both cases, because this guy here is odd, it's not going to be picked up by either this or that point here. So that's the no loss of information. And remember, the permissible interval is important because the parsers use the permissible interval, so we have to produce some number that is inside the permissible interval.
But
yeah.
the round to even is important when you're doing the backwards conversion.
It's important, but both, because sometimes, and I only realized that when I wrote my code and then I tried to run some unit tests and then some point it failed, and it's going, okay, because here there is a tie, I was taking the wrong thing, and then I saw I have to also to use round even in the other sense. I'll come to back to that later on. Okay, as short as possible. Might seem obvious, it's not that obvious. For instance, if I have these two, this number on the left is the input, and here I have two possible outputs for the input. Which one is shorter? All of them, they have 6 chars. So there is no shortest. So the rule is only the mantissa matters for this point, okay? So The exponent matters, but in direct ways. So the point here is that if the mantissa is shorter than the other, the alternative, pick the shortest one. So 1 has 1 digit, 10 has 2 digits, so we prefer the shortest mantissa. So that's what the dragon produces, okay, for this input. Another one, this one. Same thing, on the left I have inputs, on the right, 3 possible outputs. Now you know this one has a shorter mantissa, that's the one the dragon is going to produce. But what about this one? It's even shorter. Even if I don't put times 10 and put an E to represent times 10 to some power, this is still shorter. And it's true that if you print, that's what's going to get printed. But that happens after the dragon. Is more or less at the same time it runs this integer to a string conversion when it has the integer mantissa, and then at that point it might decide, oh, for this particular exponent, because it's very close to 0, maybe fixed representation will be shorter. And then it decides to print that one. But, as I said, the dragon only looks representations of the form integer times a power of 10. So deciding that it should print 0.1 is not the dragon's business. Okay? So that is out of our scope. So if you have this input, that's the output of the dragon. And there is another lesson to be taken from this slide, is we want to have the shorter mantissa. And since all those numbers are equal, having a shorter mantissa, you have a shorter mantissa if and only if it has a larger exponent. So we have an incentive to pick f as high as possible. Keep that in mind, that will be important later on for our algorithm. One more. Input on the left, 3 possible, the other possible outputs but I just printed 3 here, show it just 3 here. It's not very clear, but the number is this one here, so this one is that, and that, okay? So all the mantissas have exactly 9 digits, so there is none that is shorter than the others, but one of them is multiple of 10. And if one of them is multiple of 10, we can divide by 10, adjust the exponent, is still the same number, but has a shorter mantissa. So that's what the dragon does, okay? If we find one possible mantissa that is multiple of 10, we prefer that one because we can make the mantissa shorter. So for this input, that's the output from the dragon, okay? And
Wait, but does that round trip? Because it doesn't look like it's the closest number.
no, it's not the closest number, but all those numbers, they are still in the permissible interval. If we print that and the parser, which can be the compiler, reads that number here, it will say, oh, the closest float point number to this value here is that one. So the round trip is safe. If I go much down here, closer to the previous one that is there, then the compiler or the parser might decide to go there. But we're still in the permissible interval. So all those numbers are possible outputs. But this one is the shorter. Questions? No?
The shorter is the shortest possible is just a added bonus, or is it part of the specification of the problem?
Is part of the specification of the problem. As I said here, let me go back maybe like this. In decreasing order of importance, being shorter is favor of being close. Okay. But if there is no information loss. Okay, so, and why do we care about the shortest output. That's a convenience for us humans, because consider this number here. So again, input on the left, possible outputs on the right. So we have here something that is multiple of 10. Not only 10, 100 and 1,000 and so on and so forth. So if the dragon pick that one and remove all the trailing zeros, we end up with this thing here. And actually, that's very convenient, because if I type, if instead of the 1/3, I have typed 0.3, and I go through all those exercises, when it prints, it's going to print 0.3, not 0.300000001, which is the closest. We don't want to see that. That's why we humans want to see the shortest possible, provided that there is no information loss. And even if it's not the closest to the number that is stored. So this is for us. Okay, again, yes?
So those rules, are those the rules established by the Dragon algorithm itself, or are those rules established by some standard?
So it was as I said, so when Steele and White published their paper, they did the two contributions. First was to set up these rules, because before it was a mess. The article was published in 1990, but it was 20 years in the make. White started looking at this problem in the 70s. And first he said, what the systems are doing. And then sometimes they didn't have these round trip safety. So you could have one number, you print that number, you parse that number, you store another one. And you repeat that, you would drift away from the number that you have at the very beginning. And some guys that implement those algorithms say, but you know, float points, yeah, it's approximation anyway, what can I do about that? It's just impossible. So I think the most important contribution by Steele and White was to set up these rules, and since then, most of the algorithms, it's not that I set by a standard and etc., it was set up by this paper and they tried to do, and actually the C++ standard, if I read what is there, I think it sounds like they are saying the same thing as Steele and White. It's not very clear to me that it's exactly that same thing, but that's exactly the same thing that Ryu implemented and the three main implementation of the standard library use.
So since then, all the other implementations have basically just been refinements using those same rules. Nobody has tried to come up with some better definition of knowledge.
No, not that I'm aware of. Though it has the de facto standard. When you want to have these round trip and short as possible. Because sometimes you say, I don't care, I just want to have 2 digits. So that's it. So if you lose information, you lose information. But if you just go for this, I want to print, sometimes it's for us, right? But sometimes for persistence, maybe you want to put that in a JSON file. And then later read this JSON file, and you don't want to repeat this drifting away that was happening before Steele and White.
Do you have time for me to ask one more?
Yes, of course.
Okay, because I was confused how it could be no information loss, and yet you could still not be the closest one. And I think, so now no information loss means that you take the possible representations and you pick the one that there's no information loss, not relative to the actual number,
exactly,
but to the one that you pick, and which one can you actually represent in the string without any representation loss.
Yes.
So I think it's important that these numbers over here are not the floating point.
No, yes, exactly. These are just is in the set of possibilities that the dragon could produce. You have a question?
So to be clear, all 4 of the decimal numbers here, when parsed, will give the same byte.
We'll give the same guy here. But that's the shortest one. And so that's what the dragon produced. But if we produce any of those here, the round trip safety will be there because they are in the permissible interval. All of them is just we have to pick one. And what's the rule to pick one number in this permissible interval? So favor the shortest one, if there is one that is shorter. Otherwise, if you are all equal, then pick the closest. There might be 2 closer at the same distance, then tie break rule, round to even. All right, okay?
There are infinite.
There are infinite, yes. There are infinite possibilities. And I'm here just showing a few of them, and ends up that this one is the shortest possible because I'm just give the example that produced the shortest. But I chose the F. I chose the F that I know that's the F that is going to be picked. And we are going to see how we pick that F. Okay? And then, okay, so my dragon, I have a dragon as well, and it comes from some culture. So I want to introduce you this dragon and the culture it comes from. So following Pythagoras' advice, let's leave the roads and let's take the trails. So I'm taking you to the trails of the South American forest, and I want you to introduce you to the Guarani people. Guarani is an indigenous group of people from South America. They live in what is now known as Brazil, Bolivia, Paraguay, and Argentina. They have been struggling for the last 5 centuries, but they seem to cope a little bit better in Paraguay. They are very numerous in Paraguay. The Guarani language is one of the 2 official languages of the country with Spanish. It is spoken as a mother tongue by about half of the population. And the currency, the Paraguayan currency, is called the Guarani. Okay, so, and now let me give you a crash course in Guarani mythology. But of course, take everything I'm going to say with a pinch of salt. I'm a quant, I'm not an anthropologist. What do I know about Guarani? So, and also, even the experts, they disagree between themselves. And the main reason for that is the Guarani language was not written. It was only spoken. So when the Catholic priests from Spain and Portugal arrived in South America, they created the grammar and the spelling, and they wrote the first Guarani documents. And they were there also, they were trying to Christianize the Guarani people. And when they tried to Christianize the Guarani people, they mix elements of Christianity into they blending inside the Guarani mythology. So things that we think is basically Guarani mythology, there might some influences from Christianity in there. So it's not really the original Guarani mythology. So take everything with a pinch of salt. So at the beginning, gods Tupã and God Araci, they create the world and they create the first couple of humans, Rupavi and Sipavi. Tupã also creates 2 spirits, the spirit of good and the spirit of evil. Angatupiri was the good and Tau was the spirit of evil. Rupavi and Sipavi were given the task to populate the earth. And they have several sons, one of which was Marangatu, which was a beloved leader by his people, and had also many children, including Keraná, beautiful daughter, Keraná, and Tau, the evil spirit, fell in love with Keraná. Keraná means in Guarani, sleeping beauty, but there is no Disney here, okay? Disney didn't go to try to Christianize the Guarani people. Okay, so Tau fell in love with Keraná, and so he tried to kidnap Keraná. Angatupiri tried to prevent that from happening. They have a fight. Unfortunately, Tau won the fight, and so disguised as a handsome young man, he managed to capture Keraná. But then, Goddess Araci was really upset with this, and she placed a curse on Tau's and Keraná's sons, and they were all born as terrifying beasts. There were 7 sons, and they were all terrifying beasts. The oldest one was Teju Jaguar, or Teju Jaguar, depending if you come from a more Brazilian or more Spanish or more Paraguayan accent. So Teju Jaguar, my algorithm is named after Teju Jaguar. If it's difficult for you to pronounce, you can call my algorithm Teju or Tej if you want. My namespace is Teju, but the beast is Teju Jaguar, okay? Teju Jaguar is a terrifying beast by appearance, but is actually Tupã made it very docile. He's harmless. He only eats fruits and honey, so he's vegetarian but not vegan. And he is the lord of the caves and protector of treasures, including the algorithm he taught me. Okay? So let me talk about the Jaguar, the algorithm, finally. So remember our problem is we have the number on the right and we have to produce a number in the format of the left. We are going to start our search finding f. So again, real line, I put here our input. We are interested in produce the output for this number here. And I'm going to focus on the centered values. So the neighboring values are these two here. I just increment or decrement the mantissa. Okay, so those are the neighbors. This one is halfway, is a centered number. For uncentered values, is a bit different. But the essence is here and it's simpler. That's what I'm going to show you. And remember the permissible interval. It starts halfway between two consecutive float point numbers and ends halfway between two consecutive numbers. And pay attention that this interval here has length 2 to the e. This slide is get too complicated for me, for my taste. So let's simplify. All we need to know is that we are looking for f such that there will be a number of the form n times 10 to the f inside this interval, and this interval has size 2 to the e. And remember that we have this lesson from one of the slides, the larger f, the shorter n. So we have the incentive to pick f as large as possible to get a mantissa that is short as possible, okay? But we have to keep in mind that we cannot pick any f. There must be a number of the form n times 10 to the f that it falls inside the permissible interval. If there is none, we cannot use this f. So if there is none, if we fail, if we overshoot and pick a f that is far too large, what's going to happen is there will be no number of the form n times to the f inside the interval, but there will be one just before, one just after, two consecutive number of the form n times to the f. The difference between these two, u minus v, is 10 to the f, which obviously here bigger than 2 to the e. So if I fail, if I overshoot and pick a too large f, that inequality will hold. So if I enforce the opposite inequality, then I will be sure there will be a number of that form inside that interval. Okay? But this f has to be the largest as possible, the largest such that this inequality holds. So it means that f plus 1 cannot verify that equality. Otherwise, I would have picked f plus 1. So f verifies this equality, f plus 1 doesn't. So we have these two inequalities there on the right. And if I take log from all sides, I have these two inequalities here, which means that e times log of 2 is a number between two integers, f and f plus 1. So f is the integer part of e times log 2. That's the definition of f. That's how I pick f in the other slides. I chose 8 because I knew f has to be 8, and I just listed the numbers of the form. Actually, I can have a slide. Just bear with me 1 second. I have to remember first the extremes of the permissible interval, and the extremes of the permissible interval, they have this half here that I don't like to work with non-integer numbers. How do we fix that? How do we turn this number into an integer number? From the gesture, I understand. Yeah. Double the mantissa, decrease the exponent. That's it. We have done this trick before, right? So, but I was saying, I pick a f such that I know there will be many, possibly just one, but possibly a few points of the form n times 10 to the f inside the permissible interval. So in that slide, the previous slide, I have chosen f to be 8 because of that, and I show one of these possible points, and one of them has a lot of 0, was 3, 0, 0, 0, 0, and that was the one that ended up being produced by the dragon. So let's look at all the points of this form that are in the neighborhood of this interval, some inside, some outside. And I denote them with stars. So, and I want you to pay attention to 3 star points, 3 very important star points. A is the largest. Okay, so the correct sentence is A times 10 to the F is the largest point that is smaller than or equal to 2m minus 1 times 2 to the e minus 1. Okay, but I would say just A is the last before the left end of the interval. Okay, but you understand what I mean. B is the largest before or on this point here, and C is the largest one before or on our input. Okay, those are crucial points that we need to find. A, B, and C. So, very similar we did to F. F is the largest that's on or before that number here. So A plus 1 must be bigger. So if I divide this by 10 to the F, I have these inequalities here, and again, very similar to what we did for F. The definition of A is the integer part of this quantity here. For B, it's basically the same thing, but using this number instead of the other one. So B is the integer part of this number here, and same thing for C, by using our input here. Okay, so those are the definitions of A, B, C. So have the definition of F, we have the definition of A, B, C. Bear in mind, and bear with me. When we did that, as we did in the other exercise, in the other slide, we have to think about, is there among the star points that are inside the interval, one that is multiple of 10? Because if there is one of these big stars that is multiple of 10, then we can just remove the trailing zeros, adjust the exponent, and we have a shorter representation. So basically, if one of these star points is S times 10 to the F, where S is a multiple of 10, we can do better. And a very good candidate for S is this number here. Is a multiple of 10, because it's 10 times some integer number, so it's a multiple of 10, and is the largest number, the largest multiple of 10 that is before or is less than or equal to B. Maybe this guy is here or there, I cannot use, but maybe is one of the big star points. And if it is, I can use this number. Okay? So, having said that, this is the Ju Jaguar. Okay? If you remember that, you'll be able to write the code. I promise. Maybe you need a bit more, but that's the crucial part. If you remember that, you will be able to write the code. So, you have to return the shortest if we can, or the closest if we must, which is basically the same as the rules from Steele and White. Just a bit more precise. The shortest mean this S here. And the closest mean either C times 10 to the F or C plus 1 10 to the F. And I'm sparing details on how you decide which one is closer, just not give too much into details, but that's doable. And in here, at that point, we might also have to use the round to even rule, because C and C plus 1 might be exactly two possible solutions equidistant to the inputs that we have. Then either C or C plus 1 will be an even number, round to even will pick that one. I only discovered that when I was doing unit test. And a test fail say, nobody told me that. Okay, but I'm telling you, so if you implement the algorithm, you'll get it right from first place, first shot. Okay, and of course, when we have S of this form, we have to remove the trailing zeros, and then that's what we really return. But then we pick from S. Okay, and that's the only loop that I have in my code. And I don't know how to eliminate this loop. No other algorithm eliminates this loop. that remove trailing zeros. I think is a very, very difficult theoretical problem in number theory to find a way to do that in one go, or the one, I don't know, I use a loop. It's the only loop in my code. It bothers me, but I cannot do a PhD in number theory just to solve this problem. I cannot afford that. I wish I could. Okay, so there we are. Let's be a bit more precise when I say return the shortest if you can. Okay, so how does that work? Keep that in mind. We'll see the algorithm appearing here. Okay, I will denote s times 10 to the f with an I. Let's keep an I on that point. So and that point might be, as I said, so it cannot be bigger than b. It can be anywhere on the left of b. And so depending on where it falls, we might be able to return that number. So let's consider this possibility. S is bigger than A and is smaller than B. So the I will be inside the permissible interval. So we can return the shortest. So that's what we do. We return the shortest after removing trailing zeros. Okay, but basically we return the shortest. But what if S is not smaller than B? They must be equal to B. It cannot be larger than B by definition of S. So it's very likely that this number here is inside the permissible interval. And if that's the case, we can return that. But there is a problem. Maybe B is a tie between our number, our float point number, and the next one. And if there is a tie here, then maybe this S is the output for the other one, not for us. But if there is no tie, then we are inside the interval, then we can return S. But if there is a tie, then we have to run the tie-break rule. So if our number or our mantissa wins the tie against the next float point number that is here, then if our M wins that tie break, then we return the S. If it doesn't win the tie break, it means that this S here will be the output for the next one. Okay, it will be the output for some float point number, but not ours. Okay, but if that doesn't happen,
if it falls on the border of the and you're using the tie breaking rule, you are maintaining the representation is maintaining maintaining the back trip only if the parser
has to implement the same rule. The parser must know this rule. Okay, so that's the deal. That's the agreement between the parser and our algorithm. So that's one point also that I found a bit like not much precise in the papers. They would say a correct parser would produce the right number. I say, what does correct parser mean? And I think again it was when I was doing unit tests and it failed. So why does it fail? So okay, there's something that they didn't tell me, and a correct parser has to apply this rule as well. Yes.
The rule doesn't come from nowhere. It comes from IEEE. And so there's a reason for the ties breaking tradition.
To avoid bias.
Right? Like this isn't just a rule out of nowhere for a tie break.
For sure, yes.
Can there be more than one S in the permissible interval?
Good question. No, because 10 to the F is smaller than 2 to the E. If you have 2 inside, so the difference between these two will be at least 10 to the F, and will be greater than, so it cannot, it must be just one. That's one important point in the proof of all these things. But that's a very, nobody have ever asked me that, but that's a very good point. I have asked myself to prove that it's going to work, this algorithm. So if S is bigger than A, and nothing like this happens, so we cannot return S, so we must return the closest, which is either C or C+1. Okay? What if S is equal to A? Okay? very likely we cannot return S because most of the time A will be outside the permissible interval. But if there is a tie, we still have a chance. We have to, if there is a tie, A is a tie between our, so in the halfway between our number and the previous float point numbers, then, so if there is a tie, then we run the tie break. If our M wins, we can return S. Otherwise, including if F is smaller than A, we cannot return S. We must return the closest, either this or that. And that's it. That's the algorithm, okay? And some practicalities. I showed you the definition of F with this number here, there. But log 2 is a rational number, 0.30. I don't want to deal with that, right? So I want to deal with only integer numbers. But there is this approximation here that works for every E inside this interval here. And this interval is large compared to the exponents that appear in doubles, even for binary to 128, and I think even for binary to 156 is more than enough. And I could have used other approximations for log of 2, but I picked that one because it has the power of 2 in the denominator. So it's very cheap to, and particularly is 32. It's even cheaper. We don't have to do any bitwise shifting some systems and etc. And if you remember my talk from last year, this is an Euclidean affine function. And I use some properties of Euclidean affine functions inside the algorithm. Something similar for A is this thing here. The numerator there is 2 to the E minus 1 is an awful number. Remember the 2 to negative 149 is that kind of awful, okay? And so is 10 to the F. It's a huge number. And it's somehow, at the very beginning, the Dragon was calculating these numbers at runtime, and it was very expensive. But then since real life, no, since before, Grisu and others, they say, what if we pre-calculate something? I don't know exactly what they pre-calculate, but it's something similar to that. If you pre-calculate that, put on a lookup table, indexed by E, okay, F, maybe we should say indexed by E and F, but F is a function of E, so we just index on E, okay? And this number here, so it's basically that guy here for some K, I'll get there, but this guy here can be pre-calculated, and I just store a certain number of bits of this number. K bits, exactly. And what's K? The rule of thumb is basically twice the size of the float point type. So for floats, K is 64. It can be smaller, but 64, we get better performance for some reason I don't have time to explain. And if it's double, K is 128. But this is kind of a rule of thumb, and there is no mathematical proof that this thing really works. When I did that for doubles, I could just use set K to 64, and I could test all the, floats. I could test for all the floats. It would run 6 minutes, but at the end I say, yes, it works for all the floats if you take K equals 64. Good. What do I do for doubles? I cannot afford to do that, okay? So we don't have a mathematical proof, but we don't have a 100% human proof, but we have a computer-assisted proof. There is a computer-assisted proof that goes along this line. I cannot test all the doubles, but I can simplify the problem with a much smaller set of doubles, which is still very big for me to do the manual calculation, but doable for the computer to do that. So my code, actually not Teju Jaguar, it's outside Teju Jaguar. There is a code generator that generates this table, and when it generates this table, it proves that this table is going to work. Modulo bugs. Okay? But it's there. And so that's the most tricky part of the whole thing is this. But at runtime, The algorithm runtime is really simple. It's the one that I just showed you. And finally, so remember we have to detect ties, and to detect ties, we have to, it boils down to something like a divisibility check by 5 to the f. And for that, I use the M-inverse algorithm. Don't have time to explain, but you can look that up, M-inverse algorithm, and you might find an article that I wrote for Overload in 2019. I was very flattered that was elected the best article for Overload 2019. So it's there, and it's a beautiful algorithm. It's not mine. I was just trying to explain how compilers use the M-inverse algorithm. But they could not use it here because this f here is huge. It's not something that the compilers deal for integers or for unsigned integers. Yes.
I see that these values were for 32 and 64-bit floating points. That are there, so for 128-bit floating points, do we know what kind of number should we choose for key, and what approximation is good enough for log2?
I think we can prove that there will be always some k, maybe too large, maybe very large, not practical, that works. To find this k, it might be very, very difficult to find. We can prove that it exists, but we don't know which k. So that's what I'm saying is a kind of a rule of thumb that this works, and it works for the important IEEE standard. So it works for floats, it works for doubles, it works for float 128. I didn't try binary 256. To be honest, I don't know if even such hardware exists. And I don't have that. I don't know how to test, so I didn't bother. But up to 128, I did that, and it works. Okay, so, and then there are some optimization tricks. One for C, we don't need to calculate C the way I told you we would calculate C. We might be able to do something clever. There is also an optimization for integers that I wouldn't tell that is Teju Jaguar. Actually, some trick that we can be at the very early stage detect, is that number an integer? If so, do some between here. We don't need to go through whole Teju Jaguar. Real, by the way, does the same thing. I thought I have invented that, and then I saw it was not in Real's paper, but it was in Real's code. I said, okay, oh, never mind. It happens many times. Somebody has the idea that you have but before you. And there are other tricks here and there that also contribute to Teju Jaguar being fast. So I'm saying that it's fast. I have to show these boring benchmark slides, all presentation about the performance algorithm. We'll tell about performance. We'll show some of these benchmarks. So here is the histogram. That's the time and a collection of double-centered values and the time those take. So the population for each time. And so basically Teju Jaguar is on that side. So the more to the left, the better. Dragonbox is here. Ryu is here. It's not really a competitor for Dragonbox and Teju Jaguar. And here I just run, among this population, what is the proportion of doubles that Teju Jaguar is faster than Dragonbox? And this is 99.95%. There is 0.5% where Dragonbox is faster. I don't know why. Don't ask me. I don't know why. I didn't have time to dig deeper. Maybe if I go there and I try to be twiddling, but my main point about Teju Jaguar is simplicity. At this point, I'm not really keen in trading simplicity for 0.5% of the case, okay? Against Ryu, Teju Jaguar wins all the time. Here are some statistics. Let's just pay attention to the relative. So that's the mean time. So that's the relative mean time. So it means that Dragonbox is in average 27% is lower than Teju Jaguar, and Ryu is almost twice as lower than Teju Jaguar. That's for centered. Uncentered. Okay, here in the histogram you see Teju Jaguar and Dragonbox mixed together. Ryu is not really a competitor. but here I lose 6-1. It bothers me a little bit, but do I miss my sleep because of that? Uncentered values is a very minority population of the doubles, of the floats. For doubles is, I should have printed the number here, as if there are not enough numbers in that presentation. So it's 10 to the negative 14%. 10 to the negative 14% of the numbers are uncentered. Do I care about that? No. Maybe I can improve, but I'm not keen at this point in trading simplicity for the performance of this case, okay? And here, and in average, it's just 1% lower, okay? Real is not really a competitor, yes.
Just to be clear, the benchmarks we're talking about here are just determining the power of 10 mantissa and exponent.
Yes, exactly.
So the conversion to a string is not.
Conversion to a string is not included, and the decoding is not, No, decoding is not included. The decoding from the bits to the, I measure afterwards. When I have the mantissa and the exponent in binary, then I call the dragon, and then I start measuring. And when it finishes, I stop the measurement. Okay? But there is one important case among the uncentered. Those are the integers. So those I care about, because especially in language like JavaScript that doesn't make a distinction between integer and float point. So if it's bad, it is bad. So, but then that's why I have this final benchmark result here. Dragonbox didn't realize this trick. Adams did. I also did, so we have there. I beat Dragonbox 100% of the time because it doesn't implement the trick. But here, Ryu is the one to beat, yes.
And to clarify, the integer optimization also happens once you've got the mantissa and exponent.
Exactly, yes. Yes, at the very early stage of the dragon. So the dragon doesn't run, we just say, let me see if this is this particular case, so I don't need to run. So I still manage to beat Ryu 100% of the times, but I don't brag about that because it's really between and depend on your compiler, your CPU. Maybe if you change the compiler, you'll be the other way around. It might be the Ryu wins 100%. It's really in the bits tweedling part of the thing, and there is not much room for mathematical creativity there, okay? And here, the results, Dragonbox is really not a competitor for integers. Ryu in that case, but again, don't brag about that because I can, if I change the compiler, there you might not see, but I put there the platform when I test, it could be other way around. So basically this is it. But to conclude, let me just show you this. So far, I told you where Teju Jaguar comes from. I showed you Teju Jaguar, the algorithm. I didn't show you Teju Jaguar, the beast. So, ladies and gentlemen, or just gentlemen, it is my pleasure to introduce you to Teju Jaguar. Any comments on its appearance? It's a seven-headed beast, but it's not rocket science. So thank you very much. I want to express my gratitude towards my wife, Cristina Costa, for her continued support. I do that in my spare time. It means that she's paid the price. She's sponsoring me for doing that. My friend Lauren Schneider and Manuel Cacoya for the inputs on the slide, and for Victor Bogado, who introduced me to this problem in the first place. Otherwise, I wouldn't be here, and it's my pleasure that he's in the audience today. Thank you. And I will be very happy to answer your questions. Joe, the first thing.
So at the beginning, you said that you looked at this and thought, oh, this should be easy, and then looked at it and goes, oh, I have no idea what to do. And then all of a sudden, like, you know, out pops this thing that is much more simple than anything else that exists, and is faster than everything else that exists. So what was your aha moment?
It's okay, so I cannot pinpoint exactly when after I start thinking about that, but I can pinpoint, so I can tell you, I'm in this journey. It's about division, optimized divisions by integer in compilers. That's why I wrote the first paper in 2019. And from that, I realized, oh, okay, I can use that for the data algorithms. And then I came up with these Euclidean affine functions, the talk last year. And then I said, maybe the problem that Vito told me about, I can try that. And then it was not much longer after that. My main problem was, okay, I have these 2 to the e divided by 10 to the f. These is awful numbers and etc. But maybe it's some Euclidean affine function here I can do, and that was natural for me.
Really cool talk. Can you do the inverse problem next?
He asked me the same thing. I'm thinking. I don't promise. I'm thinking.
Because I need the inverse.
The second person asking me.
The inverse is more important.
So my question was, as you described, there's 3 stages, right? The decoding, the dragon part, and then the formatting details. And everyone's been really hyper-focused on that center piece, making that shorter and shorter. How much does this improve like the end-to-end time? Because of course, we don't just want the middle stage, right?
Okay, I don't have this benchmark. I didn't measure that, but if I can... So Stefan, he implemented that and he compared to other algorithms that he could have used, and he told that Ryu, after the whole thing, was 10 times faster than the other algorithms that he had. So, but yes, there is... I think we are reaching the stage where this dragon part is no longer the bottleneck. Maybe the other 2 parts become really the bottleneck. Maybe, okay, I mean, I do that for fun. Okay, maybe I improve 1%. I have a lot of fun. That's what I'm looking for. Okay, not maybe worth for paying somebody to get this 1%, but for fun, do it. Try at least. Any other question?
So by the way, Victor, you mentioned the issue of the scan operation has to be doing the
Yes.
That is absolutely a very valid concern. If I remember right, like a fairly recent Microsoft compiler doesn't, like they round it to, they round the ties up rather than rounding to even. So that is absolutely an issue. I also believe that something was fixed around 5 or 10 years ago. But if you're concerned about something older than that, that's certainly a possible problem. To my knowledge, there is nothing out there that properly produces something that will round trip no matter what of the common rounding directions a scanning library.
In my mind, it's just you should just ignore that the border exists. You should just pick one of the smaller representation value inside the...
That could be done, but the parser, when it parses, it might produce something. So the output of this algorithm must take into account that the parser must pick one in the middle, between halfway, and then they must be consistent in the rounding rule they use. And by the way, I'm using round to even here, but it's very easy to extend that to other rounding rules. I mean, I didn't bother because I know that is the one that most implementation use. So let me try that first, and if it doesn't work, why bother with the others? Maybe for fun. But it's very easy to extend that as well. And one of the things, Dragonbox is actually, code-wise, it's very, very well written. And all those things, it's in C++, and all this customization about the rounding mode and etc. is done through templates, policies, and etc. So it's doable. It's doable also for Teju Jaguar. I just didn't bother.
Is your reference implementation available?
Not yet, but I will soon release that on GitHub. It will be called Teju or Teju Jaguar, and it's almost ready. Almost ready. I have the generator. I have also generator read the code. So if you want to use for doubles and floats, the code is there. Just pick that code. It can be used. But if you have another type of different float point representation, maybe 16 bits, maybe these brain floats and etc., you can just generate using the generator. You just give the parameters for the representation, and then I generate the table. And I did the generator, an outside code, and I do code generation, not template meta programming, because I hope this algorithm will be implemented in other languages, in Java, in Rust, in C#, and etc. And if I go for the meta programming side of things, very complicated, a Java programmer might not be able to understand. So I'm sad to say here in a C++. I'm sorry to announce here in a C++ conference that the reference implementation is actually in C because of that. Any more questions? Thank you, everybody.